Alright, this is going to be a mashup of 5-5 and 5-6. We're going to talk about triangle congruence. We're looking at side, 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 and a hypotenuse-leg theorems first. That's what 5.5 is over. 5.6 is about two other forms of triangle congruence proofs. The other one is angle, side, angle, and then we have what's called angle, angle, side, and we'll talk about what both of those mean here in the next few minutes. We're going to start with the side, side, side triangle congruence theorem, and that simply says that if you have three sides of a triangle that are congruent to three sides of another triangle, then the triangles are congruent. You don't have to know anything else about the angles, you just have to match up the sides. So if we have my two triangles ABC and triangle DEF, if I know that segment AB is congruent to segment DE, and I know triangle or segment BC is congruent to segment EF, and segment AC is congruent to segment DF, then that means that triangle ABC is congruent to triangle DEF, and again, I don't have to know anything about the angles, I just need to have three pairs of corresponding sides that are congruent. Okay, example number one, we want to show triangle KLM is congruent to triangle NLM. And we have some given statements. Here's our drawing. So let's go ahead and get started with our statements and our reasons. And we always want to start with what's given. I know segment KL is congruent to segment NL. And I also know segment KM is congruent to segment NM. The reason for that is that it's given. Okay, and it's a good idea always to go ahead and we can kind of draw on the triangle and mark up what we have so we can see what we got towards where we're going. So KL is congruent to NL, KM is congruent to NM. Okay, and remember we want to show that the two triangles are congruent, so I have to find out something, some corresponding part that's congruent on the triangles. I happen to notice that these two triangles are kind of connected. They're touching. They share this segment LM, which is a good place to use the reflexive property. I can always say that something is congruent to itself. So I'm going to use segment LM is congruent to segment LM. That's going to be my reflexive property. Okay. Now when I do that, that's giving me my third pair of sides that are congruent. So I have my three congruent corresponding sides. That means then that I can say triangle KLM is congruent to triangle NLM because of our new side, side, side theorem. If I can spell. There you go. Alright, just a real quick review before we introduce the next theorem. Here's a right triangle. Now remember that we call the two sides that form the right angle, we call this a leg. This is a leg. So our two sides are called legs. And remember that the longest side, the side that's across the 90, we call that the hypotenuse. Okay? And here's the next theorem. The hypotenuse-leg congruence theorem, and it says that if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of a second triangle, then the triangles are congruent. So this particular theorem hinges on the fact that I have right triangles. Okay, that part is important. I have to have right triangles. So I'm going to go ahead and let angle B be 90 degrees. I'm going to let angle E be 90 degrees. All right. Next thing that has to happen is I have to know that the hypotenuse, segment AC, is congruent to the other hypotenuse, segment DF. Okay. And then I have another pair of legs that have to be congruent. So let's just say that BC is congruent to EF. Okay, so three things have to happen. I have to have two right triangles I have to know that the hypotenuse of one triangle is congruent to the hypotenuse of the other triangle, and I need to have a pair of corresponding legs that are congruent. If that's the case, then I can say that triangle ABC is congruent to triangle DEF. Okay? Again, in order for this theorem to work, you have to have two right triangles. Alright, so here's example number 2. Given that segment WY is congruent to the segment XZ, the segment WZ is perpendicular to segment ZY, segment XY is perpendicular to segment ZY. And we want to show that the two triangles are congruent. Alright, so let's get started. Gotta make my two columns, my statements and my reasons. Okay, let's start with segment WY is congruent to segment XZ. My reason is given. We go ahead and mark that. I know WY is congruent to XZ. I'm drawing my tick marks here, but remember that I'm talking about this whole line going this way. Okay, so those two are congruent. I'm also told that segment WZ is perpendicular to segment ZY, and segment XY is perpendicular to segment ZY. Okay. Now we have to go to what perpendicular actually means. That means that these two segments and these two segments both intersect at a 90-degree angle. So that's what we have to say. That this angle WZY is 90 degrees. And then going the other way, that's going to be XYZ. Okay, and that would be the definition of perpendicular. That lets us know that I have two right angles. Got a right angle there and a right angle there. Now sometimes it's useful to go ahead and separate out these two triangles so that you can see what's happening. I have WZY here, and I know I have a hypotenuse and a right angle there. And if I draw this other one, coming this other way, X, Y, and then Z right here, here's my hypotenuse and there's my right angle. Okay. So I can see what's going on. I know because I have two right angles, I'm going to try to use my hypotenuse-leg theorem. I already have the hypotenuses. Now if I look at this shape, I notice that they overlap and they share this segment ZY on both triangles. So because they have that same segment, I'm going to use my reflexive property to say segment ZY is congruent to itself. Remember that that's called the reflexive property. Which means I have my 90-degree angles, I have my hypotenuse and my legs. So now I can say that triangle WYZ is congruent to triangle XZY because of the hypotenuse-leg theorem. Okay. Alright, next we got the angle-side angle theorem, which is part of the 5.6, and that says that if I have two angles and the included side of a triangle are congruent to two angles and the included side of another triangle, then the triangles are congruent. Alright, so with this one, I have to have two angle pairs. So let's just say that I have angle B congruent to angle E, and I know that angle A is congruent to angle D. Alright. Again, kind of like with the side angle side theorem, I have this word included, right? And that means that the angles, the side that joins the two angles, that's my included side. So for this, since my angles are A and B, then that segment AB is my included side. All right, so another way to think of it is for an included side, the two angles, the two vertices make up that included side. So if A and B are my angles, then that segment AB is my included side. So if I have that, then I know that the triangles are congruent. I would say the triangle ABC is congruent to triangle DEF. Okay? So the order matters on this. I want an angle, side, angle. So here would be my angle, my side, and my angle. Those have to be connected. Like that. Alright, example number 3. We want another proof here. I know that segment AD is parallel to segment EC and segment BD is congruent to segment BC. We want to show triangle ABD is congruent to triangle EBC. Okay, so as usual we start with our givens. I know that segment AD is parallel to segment EC. And I also know that segment BD is congruent to segment BC. And that's given. Okay. So let's go ahead and mark this on our drawings here. I have remember that our arrows show that the two sides are congruent, or two sides are congruent. I know that segment BD is congruent to segment BC. Okay. Now, I already know my congruent sides. Now I have to use the fact that they're parallel. I have two parallel lines here. I'm going to use the segment DC as my transversal. So I have two parallel lines intersected by a transversal. I get a pair of alternate interior angles that are congruent. So I'm going to look at this segment, or this angle D here and this angle C. Okay. Now I'm going to call them, let's call this angle ADB. And I know it's congruent to angle BCE. Okay, and that's going to be because of my alternate interior angles theorem. Okay. Now, I'm looking for something else that's congruent. Notice that I have two lines AE, or two segments AE and CD that are congruent, or excuse me, that are intersecting. So I do have a pair of vertical angles right here. Okay, and as we know, vertical angles are always congruent. So let's go ahead and call this angle ABD is congruent to angle EBC. And I know that that is true because I have vertical angles. And we know that vertical angles are always congruent, which is going to give me my angle, side, angle. Angle, side, angle. So we've done that. We can show now, we can say that triangle ABD is congruent to triangle EBC because of my angle, side, angle theorem. Alright, for this theorem, we got the angle, side congruence theorem, and it says that two angles and a non-included side of a triangle are congruent to two angles and a non-included side of another triangle. If I have that, then the two triangles are congruent. Okay, so it can be any angle. So let's say that I have angle A congruent to angle D, and angle B is congruent to angle E. Okay, now if it says non-included, that means it's not going to be segment AB or segment DE. It's got to be something off to the side so that I'd have angle, angle, side. So let's just say that BC is congruent to EF. Okay. Again, it has to be non-included because if it was included, that would be angle, side, angle. So we're looking at angle, angle, side. Okay, if I have something like this, then I would say triangle ABC is congruent to triangle DEF. Okay, so here's a different way to show that the triangles are congruent without actually saying that all the corresponding angles and all the corresponding sides are congruent. I can take a shortcut. Alright, example 4, Given that segment HF is parallel to segment GK, and angle F and angle K are right angles, and we want to show that these two triangles here are congruent. So let's go ahead and start with our statements and reasons columns. 2-column proof. Okay, we want to start with our given, so I know HF, that segment is parallel to segment GK. And I know that angle F and angle K are right angles. I don't know if that's given. So I'm going to go ahead and mark that so I can kind of see what I have to work with. I know this side is parallel to this one. And I know that I have a 90-degree angle here and here. Okay, because F and K are 90-degree angles, I know that angle F is congruent to angle K. And my reason for that is because all right angles are congruent. Okay, there's a theorem that says that all right angles are congruent. Also, again, I have two parallel lines going this way, and they're intersected by a transversal. So I'm going to use my alternate interior angles again. So that tells me that angle H or FHG is congruent to KGH. And again, I have alternate interior angles there. So let's go ahead and call this out. We said this was going to be FHG congruent to angle KGH. And that would be by our alternate interior angles theorem. Then I know those are congruent. Okay, so I have my two right angles that are congruent. I have my alternate interior angles that are congruent. So there's my two angle pairs. Now again, these two triangles are sharing this side right here, this hypotenuse HG. So I can always say that HG is congruent to itself because of the reflexive property. Okay, so I know this side is congruent to itself, which tells me that this triangle HFG is congruent to triangle GKH because of my angle side theorem.